after the observation?
People often use telescopes, use like coronagraph instruments, which are made to try to cancel out the light. So not so much physical objects as methods to try to cancel out the starlight in the middle of what you're observing. And people work very hard on developing these tools because it's very hard.
I saw there was like a mission that's planned that has like a sunflower screen in front of a space telescope.
The star shade, yes.
Yes, a star shade.
Yeah, so there are actual ideas because this is, I'm going to come to this in a moment, but this is, so this imaging is very hard to do, and the main problem is stars. The stars are in the middle and they're very bright. And so the main problem is we have to cancel out somehow the starlight. And one idea of doing is what you're saying, which is a kind of star shade. It's pretty much physics, it's having a telescope here and a physical object somewhere far away that can kind of block out the light of the star, and then you can only see the planets that are just around it. And so putting that in space, these two objects, the star shade and a telescope, you could actually make better images like this. Now this is a future idea, not quite there yet, but it actually may happen in the next few decades or so. So these are just made coronagraphs on Earth, and so we just try to cancel out the starlight. But the point is, these systems are far away. You can see over a few years of time, they only move a little part of the orbit. So there's nothing here that's like Earth or shorter than Earth or something like Mercury. We can simply not do it. It'd be too close, it'd be too hard. And in addition, these stars also are nearby stars, so very bright stars, very nearby stars, and very young stars. And so the reason for them being very young is that when you have a young star, the planets are also fairly hot. Because when you form, you compress the planet into, you compress the gas into one planet, and it will still have a lot of energy left from the gravitational infall, and so it will still be hot. So these young planets are hot, much hotter than they would be over time, because these planets are far away, so they would become very cool planets. But if you look at them young, they're still hotter, which makes them a little easier to find. So we're typically finding these kind of planets far out, around nearby stars. That makes it a little easier in the angles. Bright stars and very young planets that are very hot. Yes?
Is this like an infrared image, or is it a filter they use here?
It is actually, yeah. I was going to come to that point in just a second. But yes. I just want to show you another one. So same idea. Again, don't worry about all of this in the middle, which is just a star and our imperfection of how to cancel the star. But then we actually have a planet. Two different filters. You can see the planet somewhere out there. This is just a very recent paper that came out just last week or something. I just want to show it. So people are doing this, but it's very hard. And again, far out, 92 AU in this case, and young systems. So, summary. Why do we only have, because we only have this for maybe 30, 40 planets. So why don't we, what is the problem with this technique, or why is this hard to do? I think I've said most of it. Anyone? You mean angular, so you're saying planets are too close to their stars? Yeah. All right?
Or stars are pretty far away.
Or stars are far away, yeah. So the angular resolution, and so they're, angular, they're very close to their stars, that's the problem. That's one part of the problem, and then the second part is, so the stars are too bright, generally. So that's, these two combined make it really hard. People in public talk, people often make these comparisons, like you get a big, stadium light, and you want to look at a fly that flies through the light or something like that, and you just see the light and you don't see anything else, because that's the problem. All right, so this is problem number one. So they're close to their stars. So, if a star is 10 parsecs, so that would be a pretty close star, we still get this problem. Like the distance between Jupiter and the Sun would be half an arcsec, and the distance between Earth and the Sun would be 0.1 arcsecond. So, even for a very close star, the angular separation between the star and a planet like Jupiter or a planet like Earth is just not that good. It's just a fraction of a degree. It's very close, and so it's really hard to separate those two things from each other. Which is why we try to look at the ones that are even further away than any of these, and at the very close stars, because of course if we go further away in space, things get even harder in terms of angles. All right? Does that make sense? And then the second problem is the brightness. So planets are pretty faint relative to their star. So Jupiter or Earth, they have a contrast of about 10 to the minus 9, which is really a lot. I mean, it makes some sense, right? Earth or Jupiter is pretty faint, doesn't really shine in any way. It has some light, but not much. On the other hand, the sun is pretty bright, so that's really the problem. You're trying to find something that's 10 to the minus 10 times fainter, but it's on the same time it's very, very close to the star. And that's really the key problem we're having here. It's a little better in the infrared. That's why you're asking which wavelength were these images. These are infrared images, because in the infrared, relatively speaking, the Earth is brighter because of the temperature, and so you get a bit of a better contrast. I mean, it's still pretty bad, but 10 to the minus 7 is a lot better than 10 to the minus 9. So you do gain a bit by going to the infrared. So that's what people usually do to make these kind of direct images. So I think I mentioned some of this already. What kind of systems do we focus on? Planets that are far away from the star, so many AUs, tens of AUs, 100 AU, something like that, because the angles get a bit better. Young planets, almost all of them are young, and that's really because they're very hot. And then these contrasts get better, because these planets are not actually at 200 degrees, they may be at 2,000 degrees, because they're still very young. That way you can still find them. That's nice, but of course it doesn't always help, because we don't only want to find young planets, but that's the ones we can actually see. And then what kind of instrument to use? Well, I think also here I already said some of that. So we use coronagraphs usually to cancel stellar light. So these are techniques to try to cancel out the light in the center and still see the light around it. Futuristic, as you said, things like starshade have been proposed to do this even better in the future, to try to block part of the light to do this better, but generally it's pretty hard. And then we use infrared instruments at large telescopes like the VLT to try to make these kind of images. And the result of all the effort has been a few dozen. I want to say 2 dozen. It's a little bit more now, maybe 30 or 40 planets known with this kind of direct imaging. And so the problem is the large majority of planets cannot be found like this.
Do you think this is like, well, I think it's like exaggerated to say it like that. Do you think this is like worthless, like too much effort for a method that's not that effective? Like you could do all this with other methods and still be like having better results, like finding more. What is your opinion on this?
Okay. So the question is, can you do it the easiest way? But can you? I mean, let me just go back. Like this planet here, at 90, do you have another way of finding it?
I'm not sure, but maybe other methods that we will see might seem more effective. I'm not sure. I think transits won't work here.
Well, yeah. Well, we'll come back to this in a bit. But yeah, transits won't work here because it's so far away that the chance of a transit is very low.
Yes.
Rate velocities won't work probably. You have to wait a long time to see anything at all.
Yes.
So it's not that easy actually to find this another way.
Okay, because this is, I would think like this is like my favorite way and the favorite way of many people, because like you're seeing actually the planet, so it's but
yeah.
Still like it's like very difficult. I'm not sure if maybe other methods could work.
I mean, it's certainly true that direct imaging has had a lot of effort for not as many planets as you would maybe like to find, and that's just the way it is. But there are real advantages as well to finding planets in this way. Certainly conceptually, I mean, we can actually see them. It's reassuring in a way. They're there. We actually see the light from the planet. And if we want to study them in some ways, it actually does help a lot that we can actually get the light directly from the planet. Every other technique we're going to see is somehow indirectly. We're usually seeing the star and inferring the planet from the star. And that's a lot harder in many ways to then study the planet, because we're only going to see the light of a star somehow, lack of light or something like that. So in terms of future, 100 years from now, we want to fully understand planets. we can hope that this will work better than it does today, because this is the way to directly get, we will get photons that we know come directly from these planets and not from the stars, somehow nothing indirectly. So if you want to study, let's say, how does this planet look like, in what is the color, when we can take measurements in different wavelengths, this is the way we can actually get the light from the planet directly without getting like some indirect way. So I think there are a lot of uses for the direct imaging ways, but it's true that they haven't paid off in as much as you would like, but I think it is in many ways the future of what we're going to do. All right. So who knows any other methods to find planets beyond direct imaging? Radio velocity, transits, astrometry. Whoa! Okay, so microlensing, astrometry, radio velocity, transits, pulsar timing. Anyone else? Anything else? Pulsar timing. I come back to it in a moment. Anything else? Anyone else? Okay, we covered the most important ones. Yeah, microlensing. Yeah, it does. So there's a figure here. This comes actually from the Perman book. It's slightly outdated, but it's trying to give you all the different methods in some distinguished ways, and also trying to count how low in mass we can go, so from Jupiter's to Earth's, and how many planets have we found. Now these numbers are obviously outdated already, but it gives you some kind of idea. So I know it's a pretty complicated figure, but I think we've mentioned most of the ways. So there's imaging here, which is what we talked about, actually making proper images. And then there's the different ways. On the one hand, here the photometry, the transits mostly. And then the other ones here are mostly dynamical ways. So the difference is photometry usually means measuring brightness of stars and observing a lack of brightness or something like that. Dynamical ways means measuring some kind of movement of stars. And there's microlensing, which most of you know more about than me now, since you've had a course on lensing. So you'll be disappointed or relieved, but I will not talk about it at all. So no microlensing this week. Okay, so did you not have a course on that? Yeah, I know. But I don't know much about it at all, to be honest. So, the general idea is that you have two stars which will align, and you have a lens star which will bend, because of its gravity, some of the light from the background star. And so you see the light of the background star lens through a star that happens to align. So usually that will just happen over time by coincidence, right? Some stars closer by will move faster, and they will happen to align. The light from the background star passes in this lens to the foreground star. That will give you a lensing event for a short amount of time. When the star passes through, you will see a much brighter star. I'm going to draw it, but I'm afraid I'm going to be wrong. My problem is, So you're observing from here. You get this background star, and then you have another star that's passing in front, right? And these are two stars, background star, foreground star. This one just happens to move past. And so over time, the brightness of this star will cause this kind of peak when it's just, when the light here is actually being lensed, you get this brightness peak. You'll see more of the starlight all focused in one point. Does that make sense? Now if there's a planet around here, this lens will look slightly different. It will have this short peak as a result of the additional planet being there, not just a star. So a single star will cause a very nice lens. An additional planet will cause an asymmetry in the lens because it's also there and it's bending more light in a different way. That is very generally the idea, and that's also about as much as I know about it. The nice part about this method is that you can find pretty small planets with it. It's very sensitive to almost any mass that's there. So you can find really small planets. The disadvantage, anyone? The main disadvantage of microlensing in terms of exoplanets? It's very unlikely. Yeah, it's worse than that, I want to say. Yeah, I mean, it's unlikely, that's fine. We can just find a planet, you know, maybe not a lot, but we can find some. But what about the planets we find?
We don't get to know any information about it?
We don't get to know any from, yeah, it's still worse than that as well. Like, let's say I find a planet with a lens here now, and now what do I do tomorrow? Can I look at the planet again? No. I mean, this lens will happen once, the star's now moved away, and I'll never get to see this planet again. So I hope I was right interpreting my lensing thing and, you know, getting the equations right. And I hope I now know the planet, but I'll never be able to see it again in any way. I mean, it's going to be some small planet which we can't really do in any other way, and so the star's now gone. It will never lens again because lensing events are fairly rare. So that's it. So we'll only really see these things once, and we can never really go back to even just confirm, like, have we really seen it right? You know, is this really a planet? What does it look like? What do we? So that is the big downside of any microlensing planets, is we can never check any of them in any way. So all of them are one-time things which we once found and which we've never seen again, which is, you know, it's not great.
And using that microlensing technique, how do we know that that's a planet and not just coronal mass ejection or something like that?
It's a good question. I don't know. You've pretty much exhausted my knowledge of microlensing now. I mean, there is some concern in some cases about planets being real, especially because some of the microlensing things have different solutions. I mean, you're trying to solve, you really see only like the brightness change, but what you're trying to understand is what was the mass of the objects, what was the orbits, and depending on how close they are, they will give a different lens. So there is some concern that in some cases, things may not be unique. Like something could be like a very close-in planet, it could maybe also be like another star a bit further out that would cause the same kind of lens. So there is always some concern that, you know, the solution you find may not be the only one, and if you reorient the orbit slightly and you can recreate a similar lens with different properties of orbit and mass. All right, so back to my figure here. It's a complicated figure, I know. So as I said, imaging, it says 60 here. I think that's a pretty optimistic number. But, you know, not everyone agrees on what's a planet here as well. A lot of these are very young and pretty large, so some of them may not. Anyway, so there's a few dozen, the direct image planets. We got the photometry, we got the dynamical methods, and then there's microlensing, which I thought you all knew about, but what have you done last week? Yeah, I know. All right, so here there's about 35. So there's quite a few lensed planets. It's still interesting. It gives a pretty unique population, but there's not so much you can do with them otherwise. So the main things I want to talk about here are, on the one hand, transits, main part of this course, and radial velocities. There's a few other dynamical ways here. These all relate somehow as well to movement of stars. The main one that was mentioned here is astrometry. So astrometry just means literally measuring the movement of stars, like actually measuring the stars move in the sky. So it's the same idea. There's a big planet around the star. It will cause the star to move, and they will both move around their center of mass. You see the movement of the star, which will tell you there's a planet. Astrometry here is going to say like 1, which I think is actually contested. Not everyone believes this is a true planet, so I want to say 0. So not really any results yet. But the future Gaia mission, which is now observing the sky, European Gaia mission, is measuring movement of stars, brightness of stars, velocities of stars very accurately. And so the big hope is that Gaia will actually find a bunch of, you know, actual planets because of movement of stars. But right now, so far, I want to say there's 0 planets in this way. And then here there is also the timing idea, which usually relates to not just directly Doppler shifts, but some kind of like, you know, light travel time differences or so on. This could be because the stars oscillate in some way, and you can see a difference in how the stars oscillate. There's a whole bunch of like different things here. Maybe eclipsing binaries. Maybe you can see the eclipses differ over time because of the planets, causing the eclipses to be late or early. There's transit timing variations, which again have something to do with timing. I'll come back to some of them and some of them not really. So there's a bunch of ways that have to do with actually timing things, and they will be different if the star is moving, and that you can use to find the planet. The most famous example, I'll show you this one in a moment, is pulsars, where you can use the timing of pulsars to actually find planets. But the two main methods are, for sure, radial velocities, the 600 here, and transits, 1,200. And the numbers change every day, but it's certainly the case that RVs and transits have been by far the most effective way, and that's mostly what this course is going to be about, not so much about most of the other methods. So let me simplify this figure a little bit. So I said there's direct image planets, a few dozen, I say 2 dozen. Michael Perryman, we should know better, says 60, so let's make it 3 or 4 dozen then. But doesn't really matter. There's only a few because it's hard, because you can only do it for far out planets, young stars. And then there's two main methods, Dopplers and transits. That's what this course is going to be about. And then everything else, I want to group it in 3 categories. We won't really talk about much of it. So microlensing, as I just said, single events, they never recur. So we're stuck with it. The timing things, I'll talk about it just briefly. In some ways, it will come back a little bit under transit as well. And then astrometry, pretty promising, but no real detections yet. With Gaia, hopefully, we get this course in a few years. 5 years from now, hopefully, we'll have a whole bunch of Gaia planets with astrometry, movements of the stars directly. For now, we're doing movement of the stars with Dopplers, so that means measuring the velocities of the stars, not the actual physical displacement of the star. All right? Everyone on board with this sort of simplified picture of the previous diagram? I think this is a little more clear in terms of what are actually the ways to do it. So this course, almost all of it is going to be on number 2 and 3. But keep in mind, essentially everything beyond these direct image planets are indirect ways. So typically, essentially everything we're doing is measuring the star. We're never measuring the planet. In this case, we're seeing the star move because of a planet. We're seeing the brightness of the star change because of a planet. We're seeing the timing of a star change. We're seeing the brightness of a star again change, microlensing, astrometry, movement of a star. In all of these cases, we're finding there must be a planet causing something on the star, and that's what we're seeing. We're seeing the star, and then we know there must be a planet, but we're never actually seeing the planet in any way. So, just to keep that in mind, whatever we're doing here is indirect. We're also always just measuring stars, and we're never actually measuring anything about the planet itself, except for the direct images. All right? So, should probably say this. It should maybe already be obvious by now, but all of these techniques are good and bad at some different things. So this is in part what the exercise this afternoon will be about, which is to figure out which technique for which kind of system. So I can't read this. Just want to point out there was this really nice paper. It's not very often that you read papers from 60 years ago, but it was this guy, Otto Struve, who made a paper 60 years ago in which he essentially predicted both ways, transits and radial velocities. He argued clearly there must be planets, and this was 40 years before we found any of them. There must even be some of them close in, and then we can see their radial velocities because we're already doing it for binary stars, he said, so we must be able to do it for planets as well. And then eclipses as well, we do it for binary stars, it must work for planets. So he predicted both of these ways as, he mentioned a few others, but he predicted those two ways as being the way to find planets, and 40 years later, don't think he's still alive, but turned out to be entirely right. So sometimes it's good to read whatever people say now, and then maybe you can do something smart in 40 years from now. This shows you, I think, my 6 techniques, main techniques, in one diagram, this is orbital distance, and this is planet mass. So these are close-in planets, close to their star, and these are very massive objects up here, right? Massive planets. So we get the solar system here, Venus, Earth, let's say this is Jupiter up here, so at quite a bit of a distance and much more massive than, for example, Earth, which is much lower in terms of mass. Everything else are the exoplanets. Perhaps the first thing to notice is that there isn't really any exoplanets essentially anywhere where we have solar system objects. I mean, Venus and Earth, there's not really anything right here in exoplanets. Most of this here, there's nothing there in exoplanets yet. And then Jupiter, I guess we can say we found things that actually are pretty similar, like to Jupiter. But mostly, even though we find a lot of planets, actually finding, sort of this part of the diagram, long period, not too big, it's pretty hard, and so that's not really what we found much about yet. Then the other thing is different colors. So different techniques, different places in the diagram. Up here are direct image planets. So because of the question earlier, like can we find them in another way? Well, that's pretty hard. We haven't found any of those in another way. They are very far out, 10 to 100 AU. Very massive objects, so these are all direct image planets. There's really not any other way to find those. So it's still nice. What else do we have? The microlens planets. The yellow dots here, they're sort of all over this diagram about here. So what this shows is we can find them around 1 AU. And we can find them at a lot of different masses, so even small planets, sort of these dots here. Smallest planets we found at this distance with microlensing. So that's nice, yeah?
In this diagram, we have only one planet discovered by AstroTwinCoLo, right?
Yeah, it's not here because I said not everyone agrees that this is a planet. I think it more likely is not. So it's not here. And I also, I didn't make this plot myself, but I wouldn't put it on there because I don't really think it is true. Yes?
Over 30 times. What is that?
Well, there isn't really much in this diagram. This is Earth mass. So Jupiter is about 300, right? And so 10 times Jupiter is about 3,000. So it's only like the very, very high part here. And so there are arguments in some cases about their true masses and where to put them. And so there's a reason this diagram is actually cut off here and not much higher because there are objects higher. But yeah, you can argue about the mass of some of these. The issue is that in some cases it's not that clear, like what the mass are of some of these objects. So some things that may be included here are actually brown dwarfs. It's always a little bit of an issue, especially also you see here the direct image planets. There's a few up here that are very, very high mass that may not actually be planets. But in some cases it's hard to say, which is why they're still on there. So different methods. Microlensing fills out a little bit everything here. Direct imaging is right up there. And then I guess the two main things we want to talk about are radial velocities, all the red dots. Radial velocities, all the green, bluish dots, and transits, all the red dots. So again, transits mostly on this side of the diagram. And this is because it's hard to find transiting planets that are far away. It's just really a lot harder to do. Come back to that in later, but like they don't transit very often because you need to have the right angle for them to be in transit, and it just doesn't happen very often. And then radial velocities, you can do things at long periods. What is a lot harder to do, on the other hand, is the really small ones. There's a bunch of dots here, but it's really hard to push out to sort of Earth in Earth orbits. So each of these techniques has its own advantages and disadvantages, and is good at something and not so good at other things. And so that's an important thing to keep in mind whenever we find planets. We need different techniques to fill out different parts of the diagram. If we were only doing radial velocity studies, then things would look quite different than now that we're doing it. But if you want to understand how many planets there are, for example, you do need to combine a lot of the data. You need to understand what every technique is good at. And so a little bit of the exercise this afternoon will also be about which technique to use if you want to find certain kinds of planets. All right? So the very first planet discovered. Anyone want to have an opinion on what is the first planet discovered? Yeah?
That was like the first exoplanet that orbited the star, like a normal star.
Yeah? True? Is it terrible? Yeah?
It was discovered by radial velocity.
First planet was discovered by rate of velocity? Yeah? So that, okay. So this is a terrible quiz question. You know, when you want to trick up an astronomer in the quiz question, ask him about the first planet because everyone starts to argue. There's different ways of what we would call the very first planet. The two most common interpretations are either this one, or that's what you were talking about, the first radial velocity planet in 95. This one was 92. And these were multiple planets, but they were around a pulsar star. So pulsar stars are stars at the end of their life. They're very compact. It's like the end of white dwarf stages. So you have very small stars. They're rotating really fast, and they're very magnetic. So what you have is they rotate, there's a spin axis like this, and their magnetic field may be different. And so as a result, you can receive radiation from this star at different moments. Like if you're, for example, right here as an observer, you will see this magnetic beam passing you by every one orbit, right? Because the magnetic beam looks like this, and the star is rotating. So if you're somewhere up here, you will see it pass every one period, right? And so because these things rotate super fast, and these are rotational periods, you know, this is in seconds, so it's a fraction of a second. So these things really do rotate very, very fast. So actually, these are often considered the most stable clocks in the universe because we can measure their periods so accurately that we can use them to time things in general. So we can receive this radiation of the pulsar every time again, and because it's just a rotation thing, it just keeps happening, and we can very accurately time how fast such a pulsar is rotating. So far, nothing so special, except that at some point, Alex Welchan here, who's now in the US, found that there is a variation in the period of that pulsar. And so here there's already subtracted the original period, and then you can see, you know, it's nanosecond scale here, so you know there's pretty small scale. And you see these differences here, up and down, which suggests that essentially this beam you're receiving from the pulsar sometimes is a little slow and sometimes a little early. So it's late and early, and so it's not always in exactly the same place as you would expect it normally. And so this was the first time anyone actually seriously argued, and convincingly at least, that this must be the result of planets. They could explain that the star is actually moving slightly because of the planets, and that's why these pulsar, or these beams, are late and early depending on where you are. And actually, you see this is, you know, there's multiple things in here, so this was actually multiple planets at the same time that were discovered. This was 92, and this was, I think, in this discovery stands, and everyone believes this is true. And there's 3 or maybe now 4 planets on this pulsar, and ever since people have looked at other pulsars and haven't really found any planets there. It's not that many pulsars, and they're hard to see, but still. So these were probably, I want to say, the very first exoplanets ever discovered. This was 92. Now the reason not everyone likes this as the first discovery is because these were really planets around a pulsar, and we don't usually consider those, you know, normal stars. They're not like the sun. They're really quite different, and so a lot of people, when they talk about the first planets, they want to talk about the first planet around a normal star, around a star like the sun, and then they wait until 95, 3 years later, when we actually found the very first planet around a solar-like star. So, you know, matter of slight debate, but this is 92. What I would say is the real first planet, like this 25 years ago. There's no good reason to say this is not a planet. It's not good if you want to like live there or something like that. It's full of magnetic radiation. You probably die very quickly. And so that's another reason why people, you know, wanted to wait for other stars and see if there's planets around, you know, more normal stars. But you know, these planets are there. It's really a good question to understand how they could have survived there at all. Because these stars have gone a lot of evolution before getting there. But anyway, they're there. That was 92. And then the first actual other planet was 95. And so 22 years, I will say 20, but 22 years ago now. I'm going to stick to my own schedule and say I'm going to take a slight 2-minute break or so before we continue with talking about the other first planet. All right, so 2 or 3 minutes, and then we'll continue.